For more than a century, the universe appeared obedient. Its vastness unfolded according to equations etched into chalkboards and confirmed by light captured from the depths of space. Galaxies gathered along invisible filaments of dark matter. Clusters formed like glowing archipelagos, and beyond them stretched an almost perfect cosmic calm. On the largest scales, order reigned. Uniformity was not just expected, it was assumed. This principle became the quiet foundation of modern cosmology. Then, a new eye opened. The James Webb Space Telescope did not look outward in the usual way. It looked backward, into time itself, into light that began its journey billions of years before planets formed, before stars like the sun ignited, before Earth existed at all. Webb was designed to study the early universe, to trace how the first galaxies emerged from primordial darkness. But within that ancient glow, something unsettling began to surface. Patterns appeared where randomness was expected. Alignments stretched across distances so immense they strained statistical probability. A structure not sharp, not obvious, but persistent emerged slowly from the data. It did not announce itself as a single object. It revealed itself as coherence across unimaginable scales. A suggestion that matter, long after the Big Bang, may still be echoing a forgotten arrangement. According to established theory, cosmic inflation should have erased such memory. Space itself expanded violently, smoothing irregularities, enforcing uniformity. Yet the faint imprint captured by Webb seems to resist that erasure. If the signal holds, it implies that something endured. A relic from the universe's earliest instance, preserved beneath billions of years of expansion. This is not a discovery that shouts, it unsettles in silence. A quiet tension between what equations predict and what the cosmos appears to remember. And in that tension lies a question that reaches beyond astronomy, whether the universe is truly as simple, as balanced as humanity once believed. The discovery did not arrive as a revelation. It emerged as an inconvenience. When the James Webb Space Telescope began its early deep-field surveys, its purpose was precise and restrained. It was built to peer into the first billion years after the Big Bang, to observe how the earliest galaxies ignited, merged, and matured within a universe still young and turbulent. Its instruments were tuned to infrared light, stretched by cosmic expansion into wavelengths invisible to previous telescopes. What scientists expected to see was complexity on small scales and smoothness on large ones, galaxies scattered statistically, their distributions softened by inflation, their apparent order dissolving when viewed from far enough away. The earliest datasets seemed to comply. Webb's first deep fields revealed galaxies packed tightly into ancient regions of space, their light distorted by gravitational lensing, their shapes irregular and violent. Star formation rates exceeded predictions. Supermassive black holes appeared sooner than models allowed. These surprises were striking, but not destabilizing. Cosmology had absorbed shocks before. Refinements could be made, parameters adjusted. Then, as the surveys widened, subtle patterns began to appear. Data analysts working across different institutions, NASA, ESA, independent university teams, noticed faint but persistent correlations in galaxy positions. At first, they resembled artifacts, slight alignment biases, calibration errors, residual noise from detector sensitivity. These were routine problems in early mission data, expected and well documented. The response was methodical. Reprocess the images, recalibrate the sensors, cross-check with alternate pipelines. The patterns remained. Infrared galaxy counts, mapped across separate sky regions, showed coherent density variations. Not clusters, not filaments in the usual sense, but extended alignments that seemed to persist beyond expected correlation lengths. The distances involved were staggering. Hundreds of millions of light years, then billions. Statistically, this should not have been possible. According to the cosmological principle, the universe becomes homogeneous when viewed at sufficiently large scales. This assumption underpins modern cosmology. It is embedded in Einstein's field equations when applied to the universe as a whole. It is supported by observations of the cosmic microwave background. Its temperature fluctuations differ by only 1 part in 100,000 across the sky. Inflation theory exists largely to explain this smoothness and early exponential expansion that erased primordial irregularities. Yet Webb's data hinted at structure where smoothness should dominate. Teams initially worked in isolation. One group examining galaxy redshift distributions noticed repeating overdensities at unexpected intervals. Another, mapping infrared luminosity functions, found correlations extending far beyond known supercluster scales. A third, comparing Webb data with older Hubble and ground-based surveys, found faint echoes of the same pattern previously dismissed as statistical flukes due to limited resolution. The independent detections were unsettling. Scientific caution demanded skepticism. Extraordinary claims required extraordinary evidence. The first step was replication. Data from different Webb instruments, NIRCam, IR-SPEC, and MIRI were compared. Different wavelengths, different sensitivities, different observational strategies. The alignments persisted. Next came cross-survey validation. Sloan digital sky survey maps were overlaid. DESI redshift catalogs were consulted. Weak gravitational lensing data was reanalyzed. Though less precise, these older datasets showed hints consistent with Webb's observations. What had once seemed like noise began to resemble signal. As confidence grew, the tone shifted from routine analysis to restrained concern. Internal discussions turned careful. Language softened. No one spoke of discovery yet. Instead, phrases like unexpected coherence and anomalous large-scale correlation appeared in draft papers. The possibility that Webb was revealing something fundamentally new remained unspoken but present. The next step was simulation. Modern cosmology relies heavily on numerical universe's vast simulations evolving billions of particles under gravity, dark matter, and dark energy. These simulations reproduce the cosmic web with remarkable accuracy. They are calibrated against decades of observation. If Webb's structure was real, it should appear at least occasionally within these virtual universes. It did not. Simulation after simulation failed to generate alignments of comparable scale and strength. Even when parameters were stretched to their observational limits, higher matter density, altered dark energy equations of state, the resulting structures dissolved beyond a certain size. The probability of Webb's observed coherence occurring by chance fell towards statistical impossibility. At this stage, suspicion deepened. The anomaly survived every attempt at dismissal. It survived recalibration. It survived independent verification. It survived simulation. And slowly, the language changed. What had begun as a technical curiosity evolved into a scientific question of the highest order. Whether the universe itself violates the assumptions used to describe it, peer review followed. Draft papers circulated quietly at first, submitted to ArcSiv with cautious titles and conservative abstracts. Reviewers responded with intense scrutiny. Could selection effects be responsible? Could foreground contamination distort the signal? Were the survey volumes sufficient to claim significance? Each challenge was addressed, not conclusively, but convincingly enough to keep the question alive. Crucially, no single researcher claimed ownership of the finding. This was not a lone revelation, but an emergent pattern recognized collectively. The absence of a dramatic moment, the lack of a single eureka, gave the discovery a different weight. It felt less like an announcement and more like a realization dawning slowly across the field. The universe, it seemed, was behaving as though it remembered something. If confirmed, the implications would reach backward into the first fractions of a second after the Big Bang. Inflation, once considered nearly sacrosanct, would face uncomfortable revision. Either it was incomplete, uneven, or preceded by unknown physics that left imprints too large to erase. The structure hinted at a pre-inflationary condition, relic patterns stretched but not destroyed by expansion. Yet at this stage, certainty remained elusive. The discovery phase was defined not by answers but by restraint. Scientists did not claim the universe was broken. They acknowledged instead that their understanding might be incomplete. Webb had not overthrown cosmology, had exposed a boundary where confidence faded into uncertainty. What was clear, however, was that the anomaly could no longer be ignored. It had crossed the threshold from curiosity to consequence. The universe was no longer behaving as a perfectly smooth canvas upon which galaxies were painted. It appeared textured at scales thought impossible. And once seen, such texture could not be unseen. The discovery phase closed not with celebration, but with quiet unease, a recognition that a telescope designed to study. The early universe had stumbled upon something far larger than its mission as structure, not merely of matter, but of meaning. A signal suggesting that the cosmos may carry memories deeper, older, and more resistant than theory had ever allowed. The shock did not come from what was seen, but from what it contradicted. Modern cosmology is built upon a quiet assumption so foundational that it is rarely questioned. The cosmological principle states that, when viewed at sufficiently large scales, the universe is the same in every direction. Homogeneous, isotropic, smooth. This idea is not philosophical optimism, it is mathematical necessity. Without it, Einstein's equations become unstable at cosmic scales, and the standard model of cosmology collapses into uncertainty. For decades, observations supported this assumption. Galaxy clusters varied locally, filaments wove intricate webs. Voids opened between them, but beyond a certain scale, structure dissolved into statistical uniformity. James Webb's observations unsettled that balance. The structure emerging from the data appeared to stretch beyond the scale where uniformity should dominate. Not slightly beyond, radically beyond. Distances measured in billions of light-years showed coherence where randomness was expected. Density fluctuations aligned across volumes so large that light itself could not have crossed them since the beginning of time. This alone was destabilizing. But the deeper shock lay in what theory demanded. According to inflationary cosmology, the early universe underwent a period of exponential expansion within the first fraction of a second after the Big Bang. This expansion stretched spacetime itself, smoothing out irregularities, erasing primordial asymmetries, and enforcing uniformity across vast distances. Inflation exists precisely because the universe looks the same in every direction. It explains why regions that were never in causal contact share nearly identical properties. It explains the extraordinary smoothness of the cosmic microwave background. If inflation worked as described, no structure of this scale should exist. The newly observed coherence appears to violate the causal limits imposed by inflation. For matter to arrange itself in such a coordinated way, information would have needed to travel faster than light. The universe would have needed to preserve a pattern from before inflation began. Both possibilities challenge established physics. This is why the discovery felt less like an anomaly and more like a fracture. Physicists searched for post-Big Bang mechanisms that could assemble matter on such scales. Gravity, while powerful, operates locally. Dark matter enhances structure formation, but it follows the same causal rules. Dark energy accelerates expansion, not organization. No known process can coordinate matter across such distances after inflation has ended. The structure seemed to imply a memory the universe should not possess. There had been anomalies before. Cosmology is not without its discomforts. The cosmic microwave background contains a cold spot, unusually large region of slightly lower temperature that resists easy explanation. Large quasar groups have been reported, extending across hundreds of millions of light-years, sometimes pressing against theoretical limits. Each of these findings generated debate, skepticism, and cautious revision. But none carried the same weight. Those earlier anomalies lived near the edge of statistical significance. Their detection depended on thresholds, selection criteria, and interpretation. Critics could argue coincidence, bias, cosmic variance. The new structure revealed by Webb, however, did not rest on a single dataset or method. Its signal strengthened with additional observation. Its scale dwarfed previous claims. Its confidence grew rather than faded under scrutiny. The difference was existential. If the cosmological principle fails even slightly, its consequences ripple through every derived conclusion. Estimates of dark energy density, the age of the universe, the curvature of spacetime all rely on large-scale uniformity. Violating it does not merely adjust numbers. It undermines the framework itself. Einstein's equations, when applied to the universe as a whole, assume symmetry. Break that symmetry, and solutions lose their simplicity. The universe becomes anisotropic, direction-dependent. Geometry itself becomes uncertain. This is why the scientific response was measured but profound. Researchers avoided dramatic language, yet the implications were unmistakable. Either the observations were wrong, or cosmology was incomplete. The possibility that inflation might require revision was particularly unsettling. Inflation is not just a theory, it is a patch that holds early universe physics together. Remove or weaken it, and unresolved problems return. Horizon issues, flatness puzzles, unexplained uniformity. Inflation is imperfect, but it works. Or so it was believed. The emerging structure raised uncomfortable alternatives. Perhaps inflation was uneven, leaving relic patterns stretched but not erased. Perhaps multiple inflationary phases occurred, imprinting structure at different scales. Or perhaps the universe existed in a pre-inflationary state whose geometry survived the expansion. Each option pushes physics into uncertain territory. More speculative interpretations began to surface quietly in theoretical circles. Some models of quantum gravity allow for long-range correlations seeded before classical spacetime fully emerged. Certain multiverse scenarios predict boundary effects large-scale anisotropies, resulting from collisions or interactions between bubble universes during cosmic inflation. These ideas had once lived on the fringe, mathematically consistent, but observationally unreachable. Now, observations seem to be approaching them. The shock deepened as scientists confronted a psychological realization: the universe might not be statistically fair. Cosmology had long relied on averages, assuming that any observer anywhere would see roughly the same universe. This democratic vision of reality was elegant and comforting. A universe with preferred directions or privileged structures feels older, more hierarchical, less neutral. It feels remembered rather than random. The tension between expectation and evidence became impossible to ignore. Workshops were convened. Conferences devoted sessions to the anomaly without naming it as such. Slides displayed correlation functions stretching beyond theoretical bounds. Questions lingered unanswered at the ends of talks, yet no collapse followed. Science did not break. It hesitated. The shock was not explosive, it was paralyzing. A recognition that the next step could not be rushed. Confirmation would require years. Additional surveys, independent instruments, patience, but the damage to certainty had already occurred. What disturbed physicists most was not that the universe was strange, but that it might be structured in a way that predates explanation. That beneath expansion, beneath galaxies and voids, beneath even inflation, there might exist an order written into spacetime itself. A pattern not imposed by physics as currently understood, but inherited. The scientific shock, then, was not merely about scale. It was about vulnerability. The realization that one of humanity's most successful descriptions of reality might rest on an assumption the universe no longer seemed eager to honor. And in that moment of hesitation, cosmology stood, exposed, facing a universe that appeared willing to reveal itself. But unwilling to be simple, the deeper investigation unfolded without spectacle. Guided instead by discipline, caution, and repetition. When a claim threatens the foundations of cosmology, the response is not excitement, it is verification. Every photon must be questioned. Every pattern must survive comparison with the past. The first step was historical James. Webb's observations did not exist in isolation. For more than 3 decades, humanity had been mapping the universe with increasing precision. The Hubble Space Telescope had already gazed into deep cosmic time, producing iconic deep-field images that revealed thousands of galaxies in what once appeared to be empty sky. Though Hubble lacked Webb's infrared sensitivity, its data formed a critical baseline. Researchers overlaid Webb's galaxy distributions onto Hubble deep field regions, aligning redshifts, correcting for resolution differences, and compensating for observational bias. The alignments did not disappear, where Webb saw extended coherence. Hubble showed faint echoes previously indistinct, previously dismissed. The older telescope had not been wrong. It had simply been blind to scale. What once looked like noise began to resemble a blurred outline of the same underlying structure. Next came the Sloan Digital Sky Survey (SDSS), had mapped millions of galaxies across a large fraction of the sky, providing one of the most detailed three-dimensional views of cosmic structure ever assembled. Its strength lay not in depth, but in breadth. Researchers cross-referenced Webb's anomaly against Sloan's large-scale maps, focusing on redshift slices that overlapped in cosmic time. The question was simple, but severe. Did this structure exist only in the early universe, or did it persist into later epochs? The answer was unsettling, though weakened by cosmic evolution. Traces of the same large-scale coherence appeared to persist across time, not as a rigid structure, but as a statistical preference, a subtle bias in galaxy distribution extending across vast volumes of space. The universe, it seemed, had not entirely forgotten whatever imprint shaped its earliest matter. Gravitational lensing provided another test. Mass bends space-time, space-time bends light. By studying how background galaxies are distorted by foreground mass, cosmologists can map the invisible scaffolding of dark matter. Weak lensing surveys using data from both space-based and ground-based observatories were reanalyzed with the anomaly in mind. If the structure was real, it should leave a signature not only in visible galaxies, but in the distribution of mass itself. The lensing maps aligned. Dark matter, though unseen, appeared to follow the same large-scale preference suggested by Webb's data. The structure was not merely luminous. It was gravitational. This eliminated one of the most comforting explanations that the anomaly arose from galaxy formation bias or observational selection effects. Matter itself appeared organized on scales beyond expectation. Spectroscopic confirmation followed. Imaging alone can deceive. Apparent alignments on the sky may arise from projection objects, separated by billions of light-years, appearing close together due to perspective. Spectroscopy removes this ambiguity. By measuring precise redshifts, astronomers can determine the true three-dimensional positions of galaxies. Webb's spectroscopic instruments provided this capability with unprecedented accuracy. The galaxies were not coincidentally aligned. Their redshifts confirmed physical proximity in cosmic terms. They occupied contiguous regions of spacetime, stretched across distances that defied inflationary smoothing. The structure was not an illusion of perspective. It was embedded in the universe's geometry. With each confirmation, the anomaly sharpened. Statistical analysis grew more rigorous. Correlation functions were recalculated. Bayesian models were refined. Cosmic variance, the natural fluctuation expected in finite observations, was accounted for. Yet the signal remained. Its confidence level increased beyond thresholds, typically accepted for cosmological claims. At this stage, skepticism shifted direction. The question was no longer whether the structure existed, but whether existing theory could accommodate it. Attention turned again to simulation. Cosmologists adjusted parameters within CDM, the standard model of cosmology. Dark matter density was increased. Dark energy equations were altered. Initial conditions were randomized and rerun. Millions of times, the simulations refused to comply, no matter how they were tuned. Virtual universes failed to generate structures of comparable scale without violating other well-established observations. Creating such coherence required breaking constraints imposed by the cosmic microwave background or producing anisotropies that simply were not observed. The anomaly resisted assimilation to understand its origin. Researchers examined the cosmic microwave background itself, the oldest light in the universe, released when matter and radiation decoupled roughly. Years after the Big Bang, the CMB serves as a fossil imprint of the universe's earliest structure. If Webb's structure had primordial roots, traces might appear there. Subtle correlations were found. They were not definitive, but they were suggestive. Slight temperature anisotropies and polarization patterns appeared weakly aligned with the direction of the observed structure. These signals lay near the limits of detection, buried beneath cosmic noise. But they hinted at continuity and imprint carried forward from the universe's infancy to its later large-scale architecture. At this depth of investigation, caution intensified. Researchers became acutely aware of confirmation bias. Teams deliberately attempted to disprove the anomaly, applying alternative statistical frameworks, masking regions of data, rotating coordinate systems. The structure persisted. Each attempt to erase it seemed only to clarify its boundaries. The edges grew clearer. This clarity brought discomfort. In cosmology, uncertainty often dissolves with more data. Here, data sharpened the contradiction. The universe was not behaving as a perfectly random realization of known physics. Attention turned to early universe conditions. If no process after inflation could produce the structure, then its origin must predate or transcend inflation itself. This possibility had profound implications. Inflation was meant to erase memory to reset the universe. A structure that survived it suggested either that inflation was incomplete or that it preserved more information than previously believed. Some theoretical models allowed for this. Certain inflationary scenarios predict non-Gaussian fluctuations, rare, large deviations from randomness, seeded by quantum fields. Others propose that inflation occurred unevenly, leaving regions with slightly different expansion histories. In these models, large-scale correlations can survive, stretched but intact. Still, none predicted coherence of this magnitude. More radical frameworks were considered cautiously. Pre-inflationary cosmology explores conditions before inflation began, when spacetime itself may not have behaved classically. Quantum gravity approaches suggest that correlations could exist across spacetime at scales unconstrained by classical causality. These ideas were mathematically consistent, but observationally speculative. Webb was changing that balance. As evidence accumulated, the anomaly ceased to feel accidental. It began to resemble a message not intentional, but inevitable. A signal carried by the universe itself, emerging only when instruments became sensitive enough to hear it. The deeper investigation revealed a crucial truth. The structure was not fragile. It did not vanish under scrutiny. It did not blur with better data. It did not dissolve into probability. Instead, it became more defined, more unavoidable. Its scale was undeniable. Billions of light years. Larger than known superclusters. Larger than theoretical limits for coherent structure formation. Large enough to challenge the assumption that the universe has no preferred directions, no long-range memory, no hidden order. The investigation also revealed something else, something human. Despite the gravity of the implications, no declaration was made. No headline proclaimed a revolution. Science advanced as it always does, slowly, skeptically, collectively. The anomaly was discussed in seminars, debated in journals, tested in silence, yet beneath this restraint, a transformation was underway. The universe was no longer a passive backdrop shaped solely by simple laws. It appeared textured at a scale once thought smooth. It appeared capable of carrying imprints across epochs, preserving information against the erasing force of expansion. The deeper investigation did not answer the mystery. It removed excuses. The structure could no longer be dismissed as artifact, coincidence, or error. It demanded explanation. Not yet, perhaps, but eventually. It stood as evidence that the universe may contain layers of organization still beyond comprehension. And as the data converged, one realization became unavoidable. Whatever this structure represented, it was not a local irregularity. It was a global statement about the universe itself, a statement written across spacetime. Waiting patiently for the instruments capable of reading it, as the investigation deepened, the scale of the structure began to weigh heavily on the minds of those studying it. Not because it was large, but because it was approaching a boundary that physics itself had drawn, a boundary defined not by instruments or mathematics, but by causality. In the universe described by modern cosmology, there exists a limit to coordination. Information cannot travel faster than light. Regions of space, separated by great distances, should evolve independently, unaware of one another's existence. This principle is not philosophical, it is enforced by relativity. Even the Big Bang does not violate it. At the earliest moments, the observable universe was compact enough for causal contact. But inflation rapidly severed those connections. Stretching space faster than light could traverse it, the newly revealed structure pressed uncomfortably against that limit, measured across billions of light years. Its coherence suggested correlation between regions that should never have communicated. The distances involved rivaled the size of the observable universe itself. In practical terms, this meant that whatever shaped the structure must have acted before inflation, or operated beyond the constraints. Inflatia was designed to enforce this realization. Marked a turning point. The structure could no longer be treated as an extreme statistical outcome within CDM, the standard model of cosmology. CDM rests on two pillars: cold dark matter, which seeds structure through gravity, and dark energy, which accelerates cosmic expansion. Together, they explain galaxy formation, clustering, and large-scale structure with remarkable success. Yet CDM also assumes a smooth, nearly featureless universe at the largest scales. The structure violated that assumption. Attempts to incorporate it into CDM required contortions that broke other agreements with observation. Increasing matter density amplified small-scale clustering but failed to preserve coherence at cosmic scales. Modifying dark energy altered expansion. History but introduced inconsistencies with supernova measurements and the cosmic microwave background. Each adjustment fixed one problem, only to create another. The model began to strain. What disturbed cosmologists most was not that CDM faced a challenge no model is eternal, but that the challenge came from precisely where the model was supposed to be strongest. Large-scale structure is where CDM shines. It predicts averages, not details. It thrives on smoothness. To find a contradiction there felt like discovering a fault line beneath bedrock. As this tension became impossible to ignore, attention turned toward the earliest possible origins of the structure. Primordial quantum fluctuations are the seeds from which all cosmic structure grows. In inflationary theory, these fluctuations arise from quantum uncertainty, stretched to astronomical scales by rapid expansion. Their statistical properties are well defined. Nearly Gaussian, nearly scaling variant. They produce a universe that is random, but predictable in its randomness. The structure hinted at something else. Its coherence suggested fluctuations larger than expected, more organized, more directional. To produce such a pattern, primordial fluctuations would need to be amplified far beyond standard predictions. Some inflationary models allow for this, under special conditions, fields interacting in unusual ways. Brief departures from smooth expansion, or phase transitions during inflation itself. But these scenarios occupy narrow theoretical corridors. They require fine-tuning. They predict additional signatures negationities, polarization anomalies, distortions in the cosmic microwave background that are tightly constrained by observation. While not ruled out, they remain uneasy fits. This opened the door to more unsettling possibilities. Perhaps inflation was not uniform. Instead of a single, smooth expansion, the early universe may have undergone uneven inflation regions, expanding at slightly different rates, preserving large-scale correlations. In this picture, inflation still occurred, but imperfectly. Memory was not erased completely. Patterns survived, stretched thin but intact. Such models exist in theory. They are mathematically consistent and motivated by attempts to unify inflation with particle physics. Yet they have long been considered unlikely, precisely because observations favored uniformity. Webb's data challenged that preference. Beyond uneven inflation lay deeper speculation. Some theorists began to consider the possibility that the structure originated before the Big Bang itself. In classical cosmology, the Big Bang marks the beginning of time. In modern physics, it represents a boundary where known equations break down. Quantum gravity theory suggests that spacetime may have existed in a different form before that boundary, a pre-Big Bang phase governed by unfamiliar rules. In such scenarios, large-scale correlations could arise naturally. If spacetime emerged from a prior state, whether a quantum foam, a contracting universe, or a phase transition, its geometry might carry imprints forward. Inflation would stretch these imprints, but not necessarily destroy them. The structure observed by Webb could be a fossil from an era beyond the reach of direct observation. This possibility carried profound weight. It implied that the universe's largest structures might encode information older than the universe as currently defined. That what appears to be expansion from nothing could instead be transformation from something else. More speculative still were ideas involving additional dimensions or unknown forces. Some extensions of general relativity allow for long-range correlations, mediated by fields that operate beyond conventional spacetime. Extra-dimensional models, inspired by string theory, suggest that our universe may be embedded within a higher dimensional structure. In such frameworks, apparent violations of causality could arise from shortcuts through hidden dimensions. These ideas remain unproven, controversial, and difficult to test. Yet the anomaly gave them new relevance. The escalation was not merely theoretical. It was emotional. Cosmologists are trained to expect surprises but not betrayals. The universe had behaved remarkably well for decades, conforming to models with elegance and consistency. This structure felt different. It did not simply add complexity, it threatened coherence. The language used to describe it began to change. No longer was it referred to as an anomaly. It became a feature, a pattern, a signal, something that demanded integration rather than dismissal. Papers began to frame the structure as evidence for a deeper cosmic architecture and underlying order not captured by current models. This shift mattered. An anomaly is temporary. Architecture is foundational. The idea that the universe might possess large-scale architecture implied design not intentional, but structural, a scaffolding underlying expansion itself, a geometry that shapes matter distribution across epochs. In this view, galaxies do not merely trace gravity, they trace history. The structure began to resemble a sentence written across spacetime. As the mystery deepened, causality remained the central concern. The speed of light, the ultimate limit, stood as both guardian and interrogator. How could regions beyond mutual contact behave as though coordinated? How could the universe arrange itself without communication? One unsettling answer emerged. Perhaps communication was not required. If the structure was imposed as an initial condition, written into the universe at birth, then coordination would be an illusion. The universe would not be reacting. It would be unfolding, like a pattern embedded in fabric before it is unrolled. This perspective reframed the problem. Instead of asking how the universe formed the structure, the question became whether the universe ever lacked it. Whether what appears as emergence is actually revelation. Whether cosmic evolution is less about creation and more about exposure. Such thoughts carried philosophical weight. They challenged the narrative of randomness that had dominated cosmology. They suggested that beneath apparent chaos lies constraint, that the universe may have preferred states, favored configurations, hidden symmetries. Yet caution persisted. Extraordinary implications demanded extraordinary evidence. The structure's size alone did not prove its origin. Alternative explanations remained possible. Undetected systematic effects, statistical misinterpretation, unknown astrophysical biases. Science advanced slowly, resisting the temptation to conclude, but the escalation was undeniable. The mystery had grown beyond a technical puzzle. It had become a question about the universe's deepest properties, about whether the laws used to describe reality are complete or merely effective approximations valid within certain scales. The structure's scale approached the limits of explanation. It pressed against the horizon of knowledge, where physics becomes philosophy and data becomes interpretation. It forced cosmology to confront the possibility that its most trusted assumptions might be provisional. In doing so, it revealed something essential about scientific progress. Not that certainty increases forever, but that understanding evolves through discomfort, through moments when reality refuses to fit expectation, through structures that appear where none should exist. The escalation marked the point where the universe stopped whispering and began insisting, not loudly, not violently, but persistently. A quiet, vast coherence stretching across space-time, demanding to be acknowledged. What once seemed like an anomaly now resembled a blueprint, incomplete, but undeniably present. A suggestion that the universe's largest patterns are not accidents of expansion, but expressions of a deeper order still waiting to be understood. And as cosmology stood at this threshold, one truth became clear. Whatever lay beneath this structure, it was not small. It was not local. It was not easily contained. It was cosmic in the deepest sense of the word. As the structure refused to dissolve, theory was forced to respond. Not with certainty, but with imagination, constrained by evidence. Cosmology had reached a familiar but uncomfortable stage where observation moved faster than explanation, and models once considered sufficient were asked to stretch beyond their comfort. The first response came from inflation itself. Inflation is not a single theory, but a family of models. At its core lies a simple idea: a brief period of accelerated expansion driven by a scalar field, smoothing the universe and seeding structure through quantum fluctuations. Yet the details, how long inflation lasted, how smoothly it unfolded, how the field evolved, remain uncertain. Within that uncertainty, theorists searched for room. Non-standard inflationary models offered one possible refuge. Some versions allow inflation to slow briefly, stutter, or interact with additional fields. In these scenarios, quantum fluctuations can be amplified unevenly, producing correlations larger than those predicted by simple single-field inflation. These enhanced fluctuations could, in principle, seed structures of extraordinary scale, rare, but not impossible. Such models were not invented for this anomaly. They already existed in the margins of theoretical cosmology, motivated by particle physics and attempts to unify inflation with high-energy fields. Webb's observations did not confirm them, but they made them harder to dismiss. What once appeared unnecessarily complex now seemed plausibly necessary. Yet even these extended inflationary frameworks struggled. To generate coherence across billions of light-years, the parameters had to be finely tuned. The fluctuations had to be unusually strong. It remained consistent with the observed smoothness of the cosmic microwave background. Too strong, and they would leave unmistakable scars in the CMB. Too weak, and they could not explain the structure. The margin for success was narrow. Another conservative possibility emerged from statistics rather than physics. Cosmic variance refers to the fact that only one universe can be observed. On the largest scales, statistical fluctuations are unavoidable. Perhaps the structure was not evidence of new physics, but an extreme realization of randomness, an unlikely outcome drawn from a fair distribution. In this view, the universe remained uniform on average, even if specific regions appeared anomalous. This explanation appealed to restraint. It required no modification of physical laws, only patience. As more data accumulated, the anomaly might fade into statistical insignificance. Yet this hope weakened as the structure's confidence grew. Cosmic variance can explain modest deviations, but the probability of such extensive coherence across multiple datasets became increasingly difficult to justify. Statistics alone began to feel insufficient. Attention then turned to dark energy, not as a late-time accelerant, but as an early influence. Early dark energy models proposed that dark energy played a more significant role in the universe's infancy before decaying to its present weaker state. If dark energy affected expansion earlier than assumed, it could alter how matter clustered, allowing large-scale correlations to survive longer than expected. Such models have been explored to address tensions in the measured expansion rate of the universe. Once again, Webb gave them new relevance. If early dark energy shaped the growth of structure, it might explain why coherence persists at unexpected scales. However, these models face constraints from the CMB and nucleosynthesis. Any early influence must be subtle, carefully balanced to avoid disrupting the universe's observed evolution. Each adjustment solved one problem and sharpened another. As conventional explanations strained, theorists looked further back beyond inflation, toward the origin of spacetime itself. Einstein's general relativity describes gravity as geometry, but it breaks down at the universe's beginning. At the Big Bang, densities diverge and equations lose meaning. Stephen Hawking and others spent decades exploring what this breakdown implies. Hawking's work on singularities suggested that the beginning of the universe cannot be fully described by classical physics. Quantum cosmology attempts to fill that gap. In some quantum cosmological models, the universe does not begin from a singular point. Transitions from a prior state of bounce, a tunneling event, or a phase change in a deeper quantum structure. In such scenarios, correlations can exist across spacetime without violating causality, because classical spacetime itself has not yet emerged. If the universe inherited structure from a pre-inflationary phase, inflation might stretch, but not erase. This possibility reframed the anomaly. Instead of asking how the structure formed, theorists asked whether it was ever formed at all. Perhaps it was not assembled by cosmic evolution, but encoded as an initial condition. A pattern written into the geometry of spacetime at birth. The idea was unsettling but not unscientific. Quantum field theory already allows correlations across space through entanglement. In the earliest moments, before spacetime behaved classically, such correlations could have been vast. As the universe cooled and expanded, they would fossilize into large-scale structure. In this light, Webb's observation resembled a fossil but ancient, silent but unmistakably real. More speculative frameworks began to surface cautiously. Multiverse theories proposed that inflation may produce many universes, each with different properties. In some versions, neighboring universes can collide or influence one another during formation. These interactions could leave imprints, large-scale anisotropies, or preferred directions embedded in cosmic structure. Such ideas had long been criticized for their lack of testability. Yet here was an observation that seemed to demand explanation beyond a single, isolated universe. A structure approaching the size of the observable universe itself invited questions about what lies beyond it, not as philosophy, but as geometry. Another speculative avenue involved phase transitions in quantum fields, just as water freezes into ice. The early universe may have undergone transitions as fundamental forces separated and fields settled into stable states. These transitions could produce defects, cosmic strings, domain walls, textures stretched across spacetime. While most such defects are constrained by observation, subtle remnants might survive at scales previously undetectable. If the structure represented a stretched topological feature, it would be neither random nor assembled, but inevitable. It would be a consequence of symmetry breaking in the early universe, preserved through expansion. Not a violation of physics, but an expression of it. These ideas carried echoes of earlier discoveries. Einstein once introduced the cosmological constant to preserve a static universe, later discarded when expansion was discovered. Decades later, dark energy resurrected it in a new form. Hawking's work on black holes blurred the boundary between gravity and thermodynamics. Time and again, cosmology had advanced by confronting contradictions rather than avoiding them. The structure revealed by Webb fit this pattern. Each theory bent under its weight. None broke completely, but none emerged unscathed. Inflation grew more complex. Dark energy became more elusive. Quantum gravity gained urgency. What united these responses was not agreement, but struggle. Theories strained to accommodate a universe that appeared less forgetful than expected. A universe that preserved patterns across epochs. A universe whose largest scales were not empty of information, but rich with implication. Throughout this theoretical exploration, restraint remained paramount. Speculation did not replace evidence. Models were tested against observation. Predictions were examined for consistency. The anomaly was not used as proof of any one framework, but as a constraint applied to all. In this sense, the structure acted as a filter. It eliminated explanations that relied too heavily on simplicity. It favored those willing to embrace complexity without abandoning rigor. It reminded cosmology that elegance must sometimes yield to accuracy. Einstein's equations still held. Hawking's insights still guided. Quantum field theory still described reality with extraordinary success. Yet the universe appeared to be asking for more, not a replacement, but an extension. Theories and speculations did not resolve the mystery. They mapped its boundaries. They showed how far current understanding could stretch before tearing. They revealed where physics remains silent and where imagination must tread carefully. Above all, they reinforced a humbling truth, that the universe is under no obligation to conform to humanity's preferred models. The structure Webb revealed may eventually find explanation within known physics, or it may demand new principles altogether. Either outcome would mark progress. For now, it stands as a challenge suspended between observation and understanding. A reminder that cosmology is not a finished story, but an unfolding one. A story written not in equations alone, but in light that has traveled billions of years to arrive,
with it.
Questions older than stars. And as theory bends to meet that light, it becomes clear that the universe is not merely expanding, it is revealing itself layer by layer, refusing simplicity, insisting on depth. The response from science did not arrive as a counterargument, but as a commitment. When the universe presents a question of this magnitude, the only acceptable reply is patience, precision, and persistence. No single telescope, no single data set, no single generation of scientists could hope to resolve it alone. What followed was not a rush to conclusion, but the slow assembly of a global effort designed to listen more carefully than ever before. James. Webb did not finish its work with the first discovery. It had only begun. Future observation cycles were immediately planned with greater intentionality. Where early surveys cast wide nets, subsequent programs focused on depth, repetition, and verification. Webb's infrared instruments would revisit the same regions of sky under different observational conditions. Refining redshift measurements, probing faint galaxies at the limits of detection, and searching for consistency across cosmic time. The question guiding these efforts was simple in form, but immense in implication. Does the structure persist when the universe is viewed again, more carefully, more completely? Each additional photon mattered. Webb's ability to observe in multiple infrared bands allowed astronomers to test whether the anomaly appeared uniformly across wavelengths. If the structure were an artifact of instrumentation or selection bias, it would distort differently at different energies. But if it were embedded in spacetime itself would reveal coherence, regardless of how it was observed. The strategy was not to prove the structure existed, but to give it every opportunity to fail at the same time. Attention turned outward to other instruments designed to map the universe from different perspectives. The European Space Agency's Euclid mission was launched with a complementary purpose: to study dark energy and dark matter by surveying billions of galaxies across a third of the sky. Unlike Webb, Euclid emphasized breadth over depth. It would not peer as far back in time, but it would trace large-scale structure with extraordinary uniformity. This distinction was critical. If the structure identified by Webb extended into later epochs, Euclid should detect its influence statistically, even if individual features were blurred by cosmic evolution. Weak gravitational lensing, Euclid's primary tool, would reveal whether spacetime itself bent preferentially along certain directions. Any anisotropy in the dark matter distribution would be impossible to hide. Euclid's maps would not confirm the structure directly, but they could falsify it. Meanwhile, on Earth, the Vera C. Rubin Observatory prepared to open its eye. Situated in Chile's Atacama Desert, Rubin was designed to conduct the legacy survey of space and time, a decade-long cadence observation of the southern sky. Night after night, it would capture the same regions repeatedly, building an unprecedented record of cosmic change, though best known for its ability to detect transient phenomena. Rubin's strength lay in statistics. by cataloging billions of galaxies with consistent depth and resolution. It would refine measurements of large-scale structure beyond anything previously possible. Patterns once lost in noise could emerge with clarity. Subtle biases could be isolated. The universe's architecture would be revealed not in snapshots, but in accumulation. Rubin would test whether the structure was an artifact of limited sampling or a genuine feature of cosmic geometry. Even older light was called upon to speak. The cosmic microwave. Background remains the most powerful probe of the universe's infancy. Future CMB experiments, collectively known as CMB Stage 4, were designed to measure temperature and polarization anisotropies with unprecedented sensitivity. These experiments would not only refine existing maps, but search for faint signals that earlier instruments could not detect. If the structure had primordial roots, the CMB might still remember tiny deviations in polarization patterns, subtle alignments and temperature fluctuations. These could provide independent evidence that the universe's earliest moments were less uniform than assumed. The challenge lay in separating signal from noise and cosmic variance from genuine anomaly. Yet the tools were improving. Supercomputing played an equally vital role. As observational data grew richer, simulations evolved in parallel. Early dark energy effects and non-standard initial conditions. Each simulation represented a hypothetical universe, born, expanded, and evolved according to specific assumptions. The anomaly served as a filter. Models that could not reproduce large-scale coherence without violating other observations were discarded. Those that survived were studied further not as truths, but as possibilities. Simulation became a dialogue with data, each informing the other in an iterative process. Crucially, no single simulation was allowed to dominate interpretation. Science resisted narrative temptation. The goal was not to find a story that fit, but to understand which stories remained plausible. Uncertainty was preserved deliberately, protected as a necessary space for discovery. The ongoing testing extended beyond instruments and algorithms. It reached into methodology itself. Researchers revisited assumptions long taken for granted. Survey strategies were scrutinized. Statistical frameworks were re-examined. Definitions of homogeneity were refined. The anomaly forced cosmology to interrogate its own tools not as flaws, but as evolving instruments shaped by context. This reflexivity mattered. It ensured that any eventual conclusion, confirmation, or refutation would be grounded not only in data, but in humility. Throughout this process, communication remained cautious. Public statements were measured. Papers emphasized limits and uncertainties. Confidence intervals were expanded rather than narrowed. The language of discovery was replaced with the language of inquiry. The universe was not being declared broken. It was being questioned. This restraint did not reflect doubt, it reflected maturity. Cosmology had learned through history the cost of premature certainty. From the steady-state universe to the first misinterpretations of dark matter, progress had often followed missteps corrected by patience. The structure demanded the same discipline. As years passed, data accumulated slowly. Patterns sharpened. Some correlations strengthened. Others weakened. Each update adjusted understanding without resolving it. The mystery endured not because science failed, but because it proceeded correctly. This was science as a living process, not a march toward predetermined truth, but an evolving conversation between theory and observation. A willingness to sit with uncertainty, to allow questions to mature before forcing answers. The response to the structure revealed something profound about scientific inquiry. It showed that when faced with the unknown, science does not retreat into denial nor leap into speculation. It expands its reach. It builds new instruments. It refines its questions. It listens more carefully. The universe was being observed not as an object to be conquered, but as a system to be understood. Each telescope, each survey, each experiment added a layer of perspective. Together, they formed a chorus, different voices, different tones, all focused on the same question. Was the universe truly uniform? Or did it carry deeper patterns woven into its fabric from the beginning? The answer was not yet known. But the process itself had already changed cosmology. It had shifted emphasis from confidence to curiosity, from closure to openness. It had reminded researchers that understanding the universe is not about confirming expectations, but about responding honestly when expectations fail. As new data continued to arrive, the structure remained suspended between possibility and proof. It was neither dismissed nor accepted, only examined again and again under sharper light. In this ongoing testing, science revealed its greatest strength. Not certainty, but persistence. A refusal to look away. A willingness to question its own foundations. A quiet determination to follow evidence wherever it leads avant, if it leads beyond the boundaries of familiar thought. The universe had offered a challenge written across billions of light years. Science answered not with declaration, but with devotion. And in that devotion lay the promise that, whatever the truth may be, it would be earned. The story does not end with an answer. It ends with a pause. Across billions of light years, structure has revealed itself quietly, reluctantly through ancient light gathered by instruments built from human curiosity and patience. It does not announce purpose. It does not explain itself. It simply exists, indifferent to expectation, unmoved by comfort. And in that existence lies its power. If the universe contains structures beyond current theory, then knowledge itself must be understood as provisional. Not fragile, but unfinished. Cosmology has never been a catalog of truths. It has been a process of refinement, a slow narrowing of uncertainty. Each generation inherits assumptions that feel permanent, only to discover their limits under sharper observation. This discovery follows that lineage. It does not dismantle science, it reminds science of its proper posture. Reality is under no obligation to be simple. For centuries, humanity has searched for symmetry in the cosmos. Circles within circles. Balanced equations. Uniform laws applied everywhere, at all times. These ideals are not arbitrary, they are born from success. Simplicity has worked. It has carried understanding from planetary motion to space-time curvature, from atoms to galaxies. Yet again and again, simplicity has proven to be an approximation rather than a destination. The structure revealed by James Webb appears to belong to that category of truths that resist. It does not fit neatly within established frameworks. It stretches them, complicates them, and in doing so, exposes the boundaries between explanation and assumption. It suggests that the universe may be organized in ways that are not immediately intuitive, ways that preserve memory across expansion. Order across chaos. This is not unprecedented. When Copernicus proposed that Earth was not the center of the cosmos, the equations of planetary motion did not immediately improve. In fact, they grew more complex before they became simpler again. What changed first was perspective. Humanity was displaced not physically, but philosophically. The universe no longer revolved around familiar ground. When Einstein reshaped gravity into geometry, the equations of motion did not merely adjust, they transformed the meaning of space and time themselves. Clocks slowed. Lengths contracted. Simultaneity dissolved. The universe became stranger, but also deeper. Each of these moments shared a common feature. They forced a revision not only of mathematics, but of meaning. The structure now under study carries that same quiet pressure. It suggests that uniformity, the comforting idea that no place is special, may be an approximation rather than a law. It invites the possibility that the universe possesses large-scale features that reflect conditions beyond ordinary causality, not design in the human sense, but structure and the fundamental sense of scaffolding that guides evolution. Rather than emerging from it, this challenges a deeply held intuition. Modern cosmology has taught that complexity emerges from simplicity, that small fluctuations grow into galaxies, that randomness, amplified by time and gravity, becomes structure. The anomaly hints at a reversal of that narrative, that perhaps complexity was present at the beginning, that the universe did not start as a blank slate, but as a patterned one. If so, then cosmic evolution becomes less like improvisation and more like revelation. this does not diminish humanity's place, it recontextualizes it. To exist in a universe that carries deep structure is not to be diminished, but to be situated. Life becomes a continuation of cosmic history rather than a statistical accident floating in emptiness. Consciousness becomes a phenomenon embedded within a universe that already possessed coherence. The emotional weight of this possibility is subtle but profound. It evokes humility, not insignificance. Not fear. The realization that the universe may be stranger than expected does not render understanding futile, it renders it meaningful. Every insight becomes a glimpse, not a conclusion. Every theory becomes a lens, not a mirror. The structure also reframes the relationship between observation and reality. For centuries, humanity believed that better instruments would simply confirm existing ideas with greater precision. Instead, history shows that improved observation often destabilizes certainty. Telescopes did not merely sharpen vision, they changed cosmology. Particle accelerators did not merely refine models, they revealed entire families of particles previously unimagined. James Webb belongs to that tradition. It was built to look deeper, but not to question foundations. Yet foundations are precisely what it has disturbed. Not violently, not decisively, but persistently. In doing so, it reminds humanity that discovery is not always about finding new objects. Sometimes, it is about encountering new relationships, new scales, new patterns that demand new questions. This is where philosophy quietly returns to science. Not as speculation divorced from data, but as reflection grounded in consequence. If the universe contains large-scale structures beyond explanation, then understanding reality requires more than accumulation. It requires interpretation. Meaning does not arise automatically from measurement. It emerges through context. The universe may be intelligible, but not necessarily intuitive. This realization places humanity once again at the edge of understanding. Not at the end of knowledge, but at a boundary where certainty fades into possibility. It is a familiar position. One occupied by astronomers before heliocentrism, by physicists before relativity, by cosmologists before expansion. Each time the edge felt like an ending. Each time it became a beginning. The structure does not answer whether the universe is intentional or accidental. It does not declare purpose or deny it. It simply resists being reduced to randomness alone. It suggests constraint, memory, continuity across scales that should have erased it. In that resistance lies a quiet invitation. To remain curious without demanding closure. To accept that the universe may never fully yield its origin, yet still reward the search. To recognize that meaning does not depend on final answers, but on engagement with mystery. Science advances not by dissolving wonder, but by deepening it. The structure will be studied for decades. It may be confirmed, reframed, or replaced by a better explanation. It may shrink under new data, or grow into a cornerstone of future theory. Whatever its fate, it has already performed its most important function. It has reminded humanity that understanding is not ownership. The universe does not belong to its observers. It reveals itself on its own terms, when it chooses, and often in ways that unsettle expectation. To study it is not to conquer it, but to listen to patterns written in light, two echoes carried across time. The final reflection is not one of resolution, but of continuity. Humanity remains a small species on a modest planet, orbiting an ordinary star in a universe that refuses to be ordinary. Yet within that refusal lies a kind of grace. The cosmos does not simplify itself for comprehension. It challenges comprehension to evolve. The structure discovered by James Webb is not a message addressed to humanity. It is a reminder of context, a signal that reality is layered, that order and mystery coexist, that knowledge expands not by reaching certainty, but by embracing complexity. In standing before this structure, humanity stands once again where it has always progressed the most, that the boundary between what is known and what is possible, not with answers in hand, but with questions sharpened. And perhaps that is the universe's most enduring gift, not to explain itself fully, but to remain vast enough to inspire understanding without exhausting it. A cosmos that does not conclude its story, but invites it to continue.